Hello, this is Miraj Patel here, and today we are going to introduce a new unit and topic. We're going to be introducing dynamics, which is all about motion. And last time we were talking about momentum, and then we reviewed 2D momentum. Now we're going into dynamics and Newton's laws. And so first, dynamics. Dynamics is the study of forces that cause systems and objects to move. So basically, dynamics is all about motion and the forces behind the motion. And a force is basically just a push or pull that causes a change in motion. And examples are common examples are like friction, gravity, and tension from a string, like if any pull is from a string is just tension. And so those are example of forces. And Newton was it basically created, uh, Newton's a big scientist behind all of this, all of the dynamics, because he has three laws of motion, which are very useful and important to solving dynamics problems. And so I've talked about a little bit about them before, but here I'm gonna actually spell it out perfectly for you. And so Newton's first law, and here's a picture of Isaac Newton, if you're wondering how he looks. His first law states that an object in motion will stay in motion, or an object at rest will stay at rest until influenced by an outside force. So basically, an object will keep doing what it's doing unless a force is exerted. So basically, you need to have a force to help change the motion of an object. And Newton's second law is pretty straightforward. It basically states that net force is equal to mass times acceleration. And so basically this is his second law, force equals mass times acceleration. And this is pretty much used to solve all dynamics problems. And we are going to solve a few at the end of this video. And so I'll show you how that works into the formulas. And his third law basically says forces come in pairs equal in magnitude, opposite in direction. And this one's pretty hard to understand, or like pretty confusing when you're first learning it. But basically, it's saying that when, like, if you push off a wall, you exert a force on the wall, and the wall pushes you. So basically, there's a force on the wall, and there's a force on, let's just say your hand is pushing the wall, so there's a force on your hand pushing back. So there's two forces, one in the wall and one in your hand. So, but they're equal, but they're opposite. That's what it's saying. And also, if you're standing on the ground, the earth is getting a force from your weight, but you are also pushing, or the earth is actually pushing back on you. So there's two forces, one on the earth and then one on your body, and but they're opposite, and they're the same magnitude. So basically, it's saying forces always have to come in pairs, but usually, and pretty much, they're always on the two objects touching or interacting, and each one has the same amount of force but opposite direction. So this one's very important when you're solving free body diagrams. You have to think about uh, the two pairs of forces. And so here we're gonna go into uh, free body diagrams. So always be thinking about these rules off to the side, and applying them to your free body diagram. And so here are free body diagrams. So this is an example of one, and this is a very simple free body diagram. And so here we're going to quickly go over the common forces and what they are, what free body diagrams do. Free body diagrams are basically pictures that help us analyze situations with forces in dynamics. And there are several forces first we have to introduce or get familiar with. The most common one is weight, which is just mass times gravity. And it always points straight down. Always does. So basically, if you have a box here, the weight is always pointing straight down. Always. Here you can see the weight, which is this W, is mg. And guess what? It's pointing straight down. But if we drew the weight on this, it would also be pointing straight down. So that's the most common force you'll probably see. Weight, weight, weight. And then it always points straight down. It's just mass times 10. So if you're on Earth. But it's always mass times the force of gravity. Normal force is the force that supports an object touching something and is always perpendicular to the surface supporting it. So most people think that normal force is always opposite of gravity and it's always straight up. That is true on flat surfaces, but if you have an inclined plane, the normal force is perpendicular to the surface, so it's out at an angle, but the weight is still down. Normal force, it's important. Do not get this confused. Normal force is always perpendicular to the surface supporting the object, but weight is always straight down. They can be opposing, but if you put an incline or any other surface, the normal force is not aligned with the weight. So most people think it's opposite of weight, but it's not. It can also be angled. And most of the time, if you have inclined planes and stuff, the normal force will always be out to the side. Friction. Friction is usually opposite of the motion, but it can also cause motion. It is always across the surface, and it's always parallel to the motion. So basically, friction, friction usually opposes motion. If let's just say a box is sliding forward, the friction is obviously to the back. But sometimes friction can actually help objects move. In fact, if friction actually helps us walk. So friction actually helps us push off the ground. But sometimes it can, help motion, and sometimes it usually stops, opposes motion. But it's always parallel to the motion. So if a box is sliding, the friction has to be parallel with the ground. It can never be perpendicular. It's always across the surface. And it's parallel to the motion always. And friction can be related to the normal force. So friction equals mu times the normal force, or the coefficient of friction. And this is the letter mu, by the way. And mu just means the coefficient of friction, or the roughness, as you can think about it. So basically, the greater the coefficient of friction, the more rough the surface is. And rough just means how hard it is to move across. It doesn't necessarily mean rough, but you can sort of think about it as the roughness. And if the coefficient of friction is 1, that means it takes the same energy or force to lift it as to push it. So this is very rare, but a mu of 1 means that it takes the same force to lift it as to push it. So that means it's very, very rough. It's better just to lift the object, or it's the same. And usually coefficients of frictions are around like 1/2 to about 1/3. So, and then ice, for example, would have a really, really low coefficient of friction, like maybe 0.1 or something. So usually most problems, it's about 0.3 or 0.4. That's about normal, but 1 is pretty high. And friction is not affected by the surface area. This is important. It's only affected by the normal force, or the force that the object's pushing down on the surface. So I mean, most people think that a greater surface area means more friction, but no, it only matters on how much you're pushing down, or the normal force. So we do not friction is not affected by the surface area with the ground. It's only affected by the force you push down with. And this is interesting, but it's actually true. And it makes sense because if the greater you push down, the greater the friction is, which is exactly what this means. The normal force is the relationship with the friction. It doesn't. There is no calculation with surface area for friction. So this is a weird fact, but it's true. And tension is a force from a string that always pulls. And strings, in most problems, if there's like two objects, usually there's a string attached. And tension always pulls away from the two objects. So like if we have a block, a string, and a block, and the string is tense, the string tries to pull both boxes in, and tension can never push because you can never like really push with the string. So tension always pulls away from the object, and it's usually denoted by a string. Okay, and here's some more rules. When a string goes through a pulley, we assume the pulleys are frictionless and massless. In AP1, we always assume that the pulleys are just frictionless and massless. So basically, all they do is just change the direction of the tension. Internal forces are forces within the system like tension, and they do not affect the motion of the object. And the reason why is internal forces affect both objects equally. So if they affect both objects equally, then they do not change the overall system. But they do change each individual object, but not the whole system. External forces are forces outside the system, or whatever you want to call it, whatever you call the system, and they do affect the motion of the object. So usually tension, if there's two blocks attached with a string in the middle, the string will not affect the motion of the boxes. But if there's a force like pushing one of the boxes, then it will. But tension, if it's between two boxes, or between two objects, and there's a force affecting both objects, then it will not change the the motion of the whole system. So this is a little confusing, but it does make sense. So just trust me on this. Internal forces may seem like they affect the object, but if they're affecting both objects equally, they do not. But external forces always do. And external forces, like a push, friction, the normal force and gravity, those usually are external. And when drawing a free body diagram, make a rectangle or a point as the representation of the object, and then draw vectors out from the center of mass, representing the forces. And remember, lengths of vectors represent the magnitude. So the lengths of the vectors should be proportional to its magnitude. So basically, if we have a heavy object and it's sitting on the ground, the normal force and the weight of it should be exactly the same length, or about the same. And let's just say a greater, like friction usually is a smaller force than the normal force. So let's just say we have that big box and it's being pushed, and the coefficient of friction is only 0.3. So the friction should be a very small arrow compared to the weight and the normal force, because remember, the friction is related to the normal force by coefficient of friction times normal force. And so if it's only 0.3, it should be 30% of the length of the normal force, but just make sure they're proportional to actually the magnitude. So always be important. It's always important to do that and think about that. So let's do an example of a free body diagram to show what I mean by all those rules. So here, a man is pushing a lawnmower with 250 newtons of force. The lawnmower weighs 25 kilograms and coefficient of friction is 0.3. Solve for the acceleration of the lawnmower. Okay, so here let's draw a simple picture of basically what's happening. A guy is pushing a lawnmower, 250 newtons, like this. So now let's draw a free body diagram of the lawnmower. So think about all the forces on the lawnmower. We definitely have weight. The lawnmower weighs something. It's on the ground. I didn't draw it here, but just imagine that there's ground here. So there's definitely a normal force. There's friction because the coefficient of friction is 0.3. So there should be friction going backwards. And there's 250 newtons that are applied. So here first you have to draw a simple representation of the lawnmower. So I just drew a rectangle. Friction is small because it's only 0.3. So the normal force and gravity should be about the same length, which they are. And the applied force is very large, and it happens to be the same as the normal force and gravity, and I'll calculate all these just in a second here. So basically you drew a small representation and then wrote down all the forces, and after you do the calculations you can accurately compare their sizes. But here, let me just show you the sizes of the forces. So the applied force, or the force he's pushing with, is 250 newtons. We have that. That was given. Gravity is always mass times gravity, or, the acceleration of gravity. So 25 times 10. So it happens to be 250 newtons, just like the applied force. The normal force is equal and opposite because of Newton's third law. Newton's third law. So if you said Newton's third law, you are correct. The normal force in this case is equal and opposite of the weight, and it's 250 newtons because it is just sitting there on the floor. And the friction is mu, or coefficient of friction, times the normal force. So it's 0.3 times 250, or 75 newtons. So now that you have these numbers, you can actually draw the arrows proportional to their magnitude. So these three arrows here on the right side should all be the same length, approximately, and friction should be much smaller than all three of these forces. So so basically, this object has a normal force 250, gravity 250, so they're balanced. The friction is small, but the applied force is so much great, so this object's definitely going to be moving to the right because the net force is to the right. So when you're doing these free body diagrams, think about the net force in both directions, and just like kinematics, we have to solve the accelerations independently in each direction. So let's just talk about in the y direction first. The net force is 0 because the normal force and gravity are exactly opposite and they're the same magnitude. So if we have two people pulling on a rope with the same force, the rope isn't going to go anywhere. Same thing in this case. So in the y direction, there is no acceleration. In the x direction, however, I told you that since the net force is basically the subtraction because these are opposite directions, so 250 minus 75 newtons is 175 newtons. And so basically, there's a net 175 newtons, sorry, to the right. So this object's definitely going to move to the right. And so if we use Newton's second law, net force, or the summation of the forces equals mass times acceleration, and we solve for A, so we just divide both sides by m, mass, we basically have to divide the net force, which we just calculated, 250 minus 75, so 175 divided by 25, or the mass of the lawnmower. And we get a quite large acceleration. This guy must be very strong. And so, so we get a acceleration of 7 meters per second squared. So this is a very, very fast acceleration. So, so basically, we drew a free body diagram, calculated the forces, and then we summed the two forces in. And remember, call up positive, right positive. So these two are positive, these two are negative. So in the y direction, there is no acceleration because they're both opposite, equal opposite, no acceleration. But in the x direction, the right is much stronger than the left. So 250 minus 75 gave you the net force, and then we plugged into Newton's second law. We know the mass of the lawnmower, and we solved for acceleration. Okay, so let's solve a second problem, and this problem's a little bit more involved because I put a string and a pulley, and we have two masses. So I went ahead and gave you the whole scenario, and so basically we're first gonna draw two free body diagrams for both of the blocks, and solve for the net force in both free body diagrams, and then we're going to use a systems of equation to solve for the acceleration. And so this is like an outline of the problem, and so here I'm going to show you how that looks. So first, let's go ahead and draw a free body diagram for the 10 kg block on the table. So it's sitting there, so there's definitely normal force and gravity, and they're equal. And so gravity is straight down and always mass times gravity, or 10 times 10, or 100 newtons. The normal force is equal and opposite because it's sitting on the table. So it's definitely being supported with its weight. So it's also 100 newtons because it's equal and opposite. And this is because of Newton's third law. So be sure to be thinking about Newton's laws and why it is the way it is. So friction is related to the normal force by the coefficient of friction. So if we multiply the coefficient of friction, which was 0.3, times the normal force, we get 30 newtons, which is the friction. And on this free body diagram, I should have drawn the friction much smaller, but it's definitely a little shorter than the normal force. And tension is greater than 30 newtons. And I forgot to tell you this, but in this situation, the acceleration is going to the right. So this 10 kg block, is sliding downwards. And always, when you're writing acceleration vectors, always draw it outside the objects. So always draw it away from the objects. Don't draw it like forces which are on the object. So because the object's accelerating to the right, we know that the tension must be greater than 30 because the tension is winning over the friction, and it's pulling the whole block to the right. And so now if we label our free body diagram, the normal force is 100, gravity is 100, friction is 30, but we are not sure about the tension because we don't know how fast it's accelerating. So we cannot solve for the tension. But we're going to use the systems of equation. And I'll show you what that means in just a second. So let's write a equation for this box here. So basically, because the normal force and gravity are both the same, we know the acceleration is not up and down. So I went ahead and just wrote it out for the x direction. And since the sum of the forces equals mass times acceleration, if we write an expression, friction, pretty much if the friction subtracted from the tension, we get mass times acceleration. So friction's to the left, so it's negative. Tension's to the right, so it's positive, equals mass times acceleration. Negative 30 because the friction's 30 to the left, plus the tension equals 10 kgs times the acceleration. So I just plugged in what we had into this little generic equation. So now we're going to do the same for the 5 kg block, which is going to be much simpler. There's only two forces, tension and gravity. Gravity's mass times 10, basically, on Earth. So 5 times 10 is 50. Tension is unknown, but it's less than 50. And why is that? And this is because the 5 kg block is pulling the other block down. So basically the gravity from the small block is pulling everything down. So basically 50 newtons has to be greater than 30 whatever the tension is. And so now we know that the tension's between 30 and 50 based on the friction and the gravity. Because the block is sliding downwards, the tension must be less than the block because the block is winning over the string. If the tension was greater or the same, then that one block, the 5 kg block, would not move at all. So we know that the tension's less than 50 but greater than 30. And so if we do the summation of forces, or net force equals mass times acceleration, and the two force, we only have one option, the y direction, because there's no forces in the x. So the tension minus the gravity equals mass times acceleration. And I did the same thing, substituted what I have, so tension minus 50 newtons equals 5 because it weighs 5 kgs times acceleration. And here I have this one equation for this block, and recall the other equation for the other block that looked just like that but with different numbers. And now we're going to combine these two formulas and we're going to solve it just like in algebra class. So here are the two equations I got from the free body diagrams, and I'm going to subtract the equations to cancel out the tension, because this is a systems of equation, and remember, if we have two equations, we can have two variables, but we need to solve for one of them, and we want to solve for acceleration. So let's go ahead and just cancel out the tensions, and we'll solve for the acceleration. So we have the two equations, and I subtracted this from the top one, and I just drew them on top of each other so it's easy to visualize. So if we subtract negative 50 from negative 30, we're basically adding 50, so negative 30 plus 50 equals 20. Tensions cancel out because they're both positive, and I subtracted the second one from the top. 10 minus a negative 5 means add a 5, so 15 times the acceleration. So, which makes sense because the total system weighs 15 kilograms. So if I divide each side by 15, I'll get the acceleration, which is 1 1/3 meters per second squared. And so this is the correct answer, but we can also solve this as a system. So if you want a quicker way to solve this problem, you could also think of this. You can think of this scenario as a whole system and solve it all together. And honestly, it takes way more, less steps to solve as a system. But you would first, need to understand why this all works. So basically, I'm going to cancel out the normal force and the weight of the second block, of the 10 kg block, because they do not affect the acceleration, because acceleration is to the right. So, and it's only affected by this friction here and the weight of the box here. And so if I cancel them out because they do not affect the acceleration because they're equal and opposite, the tension is internal, so it has no effect on the motion of the system. So this is where Newton's or internal forces come into play. So because the tension's pulling both blocks equally, this does not affect the motion of the system. All it is basically holding these blocks together. There are only two forces, the weight of the small box or block and the friction from the 10 kg block. So we do the same thing, summation of the forces equals mass times acceleration. So basically the friction, because friction's trying to oppose the acceleration, and then minus the weight equals mass times acceleration. So so basically friction and the weight have to be opposing each other. And as long as you subtract one from the other, you'll get the right answer. Just the sign will be different. And since the collective mass, now we're solving as a system, it's 10 plus 5 or 15, and the friction was 30, weight was 50. So we just subtract those two, and we get the same thing except the negative here. And so if we divide both sides by 15, we definitely get acceleration of 1.33. And it's okay if the sign was different like this. You just have to know which direction the acceleration is. And since I told you the box is moving downwards, we know this whole system's accelerating to the right. So the answer is pretty much the same, but we just solved it as a system instead, and it took by far way more less steps than the other one where we solved them individually and then brought them together. So solving as a system is a useful tool when solving dynamics problems. But be sure to know how to do it both ways, individually and as a system. So thank you for watching my physics video today. And so today we talked about Newton's laws and free body diagrams. So we talked about his 3 laws of motion, and we applied it on a free body diagram problem. And tune in to the next video to learn about Newton's laws in circular motion. So then we're going to talk about centripetal acceleration, and we're going to introduce maybe a few more, a little bit more challenging problem. And please, if you enjoyed this video, as always, please share it with your friends and other people that are taking physics. And email me any questions about the material and comments at mpatelbuccaneer@gmail.com. And as I told you before, Rice University has this free online textbook called OpenStax. And on that, there are plenty of dynamics problems for you to practice. And I would suggest to find some kind of problem and work it out. And if you do not understand a problem, keep on working it out until you can do it without any help. That really helps to solidify your knowledge on anything that you do in physics, at least. And if you are also taking chemistry, please visit my tutorials, buccaneerchemistry.weebly.com. And so I hope this helped you, and I hope to see you next time. And thank you for watching.